Today we're going to talk about projectile motion. Projectile motion occurs when an object is moving both horizontally and vertically at the same time, and gravity is the only significant factor causing the motion to change at all. An example of this would be shooting a basketball. So here what I've got is, this was from a video of shooting a basketball. A person shoots a basketball, it follows this trajectory. There's the ball there, you can see that. So what I did here is I traced the dots to mark the position of the ball at specific equal time intervals. So what we can see from this is this trajectory forms a shape that we know and love. We call it a parabola. So I have a nice parabola there. What I want to do is I want to draw arrows. I'm going to draw arrows from each dot to the next. It has to go over a certain amount and then up a certain amount. So I'm just going to draw little arrows here to indicate that's how much it goes over, and that's how much it goes up. So I'm going to do the same thing here. So it's going to go over about that much, and up there, over, and up. Then this one goes over, and this one goes over and down. And then this one gets a little tricky to draw this like this, over that, and down like so. Over and down, over and down like so, and then over and down. So take just a minute and look at the arrows. Notice I've separated the horizontal and vertical arrows. So what we have basically, this is a motion map, right? So the motion map, dots show position, arrows represent velocity. But because it's moving both horizontally and vertically, what I've done is I've separated out the horizontal and vertical arrows to indicate the horizontal and vertical velocity separately. Okay? So you'll notice on the vertical arrows, on the way up, those arrows get shorter and shorter. On the way down, the arrows get bigger and bigger. That makes sense. If I throw a ball straight up in the air, on the way up it's getting slower, and on the way down it gets faster. So the vertical one makes perfect sense. Look at the horizontal arrows. The horizontal arrows appear to be about the same size the whole time. So what this tells us is that the horizontal motion and the vertical motion of a projectile are completely independent of each other. They're not related. And so, because these arrows are the same size, I can deduce that the horizontal component of the velocity of a projectile is constant. The vertical velocity is changing. Why does the vertical velocity change? That's right, because of gravity. So now that we know this about a projectile, that the horizontal and the vertical motions are independent of each other, we can see then how to approach solving a projectile motion problem. We're going to separate out or split the horizontal and vertical components of everything and then apply our equations of kinematics. So we split horizontal and vertical motions, and then we're going to solve them separately. Horizontal motion, we know we have constant velocity. And vertical motion, we know we have acceleration of gravity, which for the Earth we know is 10 meters per second squared downward. 9.8, whatever you want to use. We use 10, makes the math a little bit easier, and it's pretty close. So if I have a problem, let's say got a table here, and I have a ball, and it's rolling across the table. It's going to roll off the edge of the table at 5 meters per second, and the table is 1.4 meters tall. Well, if I want to know what's going on here, what's going to happen when it leaves the table, it's going to start following a parabolic trajectory. It's going to hit the ground somewhere over here, right? I would like to know how far from the edge of the table does it hit. I'm going to call this delta x. So, to solve a problem like this, I am going to split my horizontal and vertical. So I'm going to actually write out my horizontal and my vertical. Now horizontal, I remember I've got constant velocity. Constant velocity means I have delta x, v, and t. Those are my only variables. Because remember, for constant velocity, delta x equals vt. Right, displacement equals velocity times time. When it's constant, that's what we have. So delta x vt. Vertically, I'm accelerating, so I'm going to have my whole set of variables. V naught, v, a. I'm going to use delta y because it's vertical. Okay, the vertical displacement, delta y, and t. I know vertically the acceleration is due to gravity, and that's going to be 10 meters per second squared in the downward direction. I'm going to, of course, use arrows so that I know if I need to worry about any negative signs. So then I'm just going to fill in the pieces that I know. At the beginning, the horizontal velocity as it leaves the table is 5 meters per second. And because the horizontal velocity is constant, I know that 5 meters per second is going to be the constant horizontal velocity, 5 meters per second. I also know that if it's rolling horizontally when it leaves the table, what is my vertical initial velocity? Well, if it's rolling horizontally, that means it's not moving vertically at the instant it leaves the table. So a horizontal launch projectile has an initial vertical velocity of 0. And this 1.4 meters, I can see, is going to be a vertical displacement. Now, is it up or down? It's down. Displacement is all about how far it is at the end from where it started. It ends 1.4 meters below the starting point, vertically. So that is a downward displacement. So here I am. I've written everything I know. I'm ultimately looking for this delta x, the horizontal displacement. In order to find that, I'm going to need to know the time. And that's where the magic happens. The time the ball is traveling through the air horizontally is the same as the time it's traveling through the air vertically. Time is the variable that connects the horizontal and vertical motions of a projectile. So a typical approach, I split the problem into horizontal and vertical. I put everything I know in terms of horizontal component stuff and vertical component stuff. I'm going to solve for time, whichever side I have the information to solve for time. Once I have the time, I can use the time for the other part of the problem. In this case, I'm going to solve vertically for time. And once I have the time, I'm going to use that to solve the horizontal problem. So if I solve vertically for time, looks like I don't need v. So I'm going to use my good old don't need v equation, which we all know and love. Don't need v is delta y equals v naught t plus 1/2 a t squared. Right? Again, delta y as opposed to delta x because we're talking vertical displacement here. So now I plug in the things that I know. Everything is down. I'm just going to call that positive. If you'd like to call down negative, that's fine. Just make sure both of them are negative. So I have 1.4 equals 0 times t is just 0, plus 1/2 times 10 is 5. So I have 1.4 equals 5t squared. So I simply divide by 5 and square root it. So the square root of 1.4 divided by 5 is going to be my time. So I'll get out my calculator, push some buttons. The square root of 1.4 divided by 5 is 0.529. 0.529 seconds, that's my time. So now that I know the time, I can plug that in up here. And I can solve this problem. Delta x equals vt. So delta x equals 5 times 0.529. And I just times 5. And I get 2.65 meters. That is my delta x. So you'll notice in solving a projectile motion problem, basically it involves splitting your horizontal and vertical, identifying your variables, and then make sure that the horizontal variables are just horizontal components, vertical variables are just vertical components. I'm going to end up solving one of them for time and then using the time to solve for the other one. So that is an example of how to solve a horizontally launched projectile motion problem. What if it's not a horizontal launch? What if instead of a table we have a ramp? And our same ball is launched at 5 meters per second at a ramp that has a 30-degree angle. Well, then the projectile is going to follow a nice parabola like so, right? It's going to land over here. And if I'm looking for delta x, again, let's just solve it the same way. So I'm going to split my horizontal and vertical. Horizontally, I know I have delta x, v, and t. Those are my only variables. Constant velocity, horizontal. My vertical, I have v naught, v, a, delta y, and t. And I know the vertical acceleration is 10 meters per second squared in the downward direction. What else do I know? Well, let's have this be the same 1.4 meter height from which it's launched. So I know that the vertical displacement will be 1.4 meters downward because it's going to end up on the ground, and it was launched at the top of the ramp, 1.4 meters. So at this point, that's what I know. But I have this 5 meters per second, and I can take that 5 meters per second and this 30-degree angle, and I can split that into its components. So here I have this velocity vector, 5 meters per second, 30-degree angle. So I'm going to draw the triangle. This would be Vx, the x component of that. This would be Vy, the y component of that. Vx is the adjacent side, so it's going to equal hypotenuse times cosine. So Vx equals 5 cosine 30, and Vy, being the opposite side, will equal hypotenuse times sine of the angle, hypotenuse sine 30. Well, this one I happen to know is 2.5 because that's a 30, 60, 90 triangle, and I know that the short leg is half of the hypotenuse. And this other one, I'm going to push a few buttons. Because I'm doing sine, I'm going to hit my mode, make sure I'm in degree mode, which I am. Good. Then I'm going to say 5 cosine 30, and I get 4.33. Just to double check, because sometimes I make mathy mistakes, 5 sine 30 is in fact 2.5, so we're good to go there. Now, the key here is once I found these components, Vx represents my horizontal starting velocity. But because the horizontal velocity is constant, this is my horizontal constant velocity. So on the horizontal, I'm going to put the 4.33. The vertical Vy here represents the velocity, y component of the velocity when it leaves the ramp. Well, that's the initial y velocity. So this 2.5 becomes the initial vertical velocity. And that is an upward angle. Right? And so because this is upward and these are downward, I am forced to choose a negative direction. I usually default to down as negative if I'm forced to make that choice. So down, acceleration is negative, and displacement vertical is negative as well. So what I'm going to do now is I'm going to solve vertically for time, and then use that time to solve the horizontal problem. Because I'm looking for the delta x here. Okay, so I'm going to use, of course, don't need v. Good old friend. Delta y equals v naught t plus 1/2 a t squared. So delta y is negative 1.4 equals 2.5 times t. Half of negative 10 is minus 5 t squared. And at this point I recognize this is a quadratic. So I need to do this quadratic and solve it my favorite way, which is quadratic formula, graphing, completing the square, guess and check, factoring, whatever method you want to choose. I like using the quadratic formula or the graphing. I programmed it into my calculator to make life really easy for me. You can Google that, how to do that, by the way. It's pretty easy. So first thing I need to do is put this in standard form. So I'm going to say, okay, that's minus 5t squared plus 2.5t plus 1.4 equals 0. In other words, I add 1.4 to get it over so everything's on the same side, and then I set that equal to 0. Okay? So my a is negative 5, my b is 2.5, my c is 1.4. Let's go to my calculator where I have it programmed. Oh, not on this calculator. Okay, so I'm going to go, my other calculator has it programmed. So I'm going to do it the other way. I'm going to graph it. So I'm going to clear out my graphs, whatever graphs I've got going on here, clear those out. So I'm going to enter this one, minus 5x squared plus 2.5x plus 1.4. Graph it. There's my parabola. I'm going to zoom in a little just so I can see what's going on. So I'm going to zoom in. Okay, so here we can see it. So I've got two solutions. One of them is negative, one of them is positive. Obviously, I want the positive solution. It's going to hit the ground after I launch it, not before. So I want the positive solution. So now I do, on my calculator, I do second calc. I'm going to calculate the 0. In other words, where the function value is 0. It's another name for the x-intercept. And it says to choose a left-bound point. This flashing cursor is to the left of my solution that I want, so I'm going to push enter. Now it asks me for a right-bound, so I'm going to push the little arrow, zip along my way until I am to the right of the point in question. And it says guess, and it's going to find it, so there it is. 0.835. So t equals 0.835 seconds. Got that the graphing method there. So 0.835 seconds, and so delta x equals vt. Delta x equal 4.33 meters per second times 0.835 seconds. So 4.33 times 0.835, and I get 3.62 meters. Delta x equals 3.62 meters. So that is how you solve a projectile motion problem for an angled launch. So if there's an angle, basically all that's different is you split your whichever vector is in an angle, usually it's the initial velocity, split that into horizontal and vertical components. The horizontal component becomes the horizontal constant velocity. The vertical component becomes the vertical initial velocity. Then it's a matter of being careful to keep track of your directions, which ones are positive and negative. I like to go with the arrows first and then decide what direction is negative if I need to. Then I'm going to solve for time and use that time to solve for the horizontal. And that is how you solve projectile motion problems.